And thank you.
Great. Yeah. Thank you for the opportunity to speak to you, and thank you for coming. So today I'll be talking about one sub area of my research, which is the magnetized three-wave interactions. So I will tell you why we want to study magnetized three-wave interactions, and I will get to how we manage to have a theory and simulation, and they match up very nicely by plasma physics standards. And then we are having some ongoing experimental campaign at the Omega facility. At the end, I will briefly mention those. Okay, so why do we want to study laser plasma interaction with a magnetic field? So the entire field of laser plasma interaction is unmagnetized for many decades. Because the magnetic field is very small, it doesn't matter. So all you have is a plasma and lasers shooting at them. But in more recent years, people have been working on those called the magneto-inertial confinement fusion concept. For example, the first one is, for example, pursued at the Sandia National Laboratory, where they implode a cylinder by running currents through parallel wires. You have the J cross B force imploding things, generating X-rays and fusion, and potentially neutrons and so on. So that's a case where you have a magnetic field, obviously, but then you also have a laser. And the point of having a laser there is to do the preheat. Because just by having the magnetic compression, they're not able to get to the temperature for fusion, so they have to have extra heat, which is provided by the laser. So another concept, which is primarily pursued at the Lawrence Livermore National Lab, is the indirect drive to fusion. So in the usual approach, you have this gold can here, and you shoot your lasers in the can and make X-rays, and the X-rays implode a capsule, which is maybe at the very center of it, and that's the approach that have people gotten to fusion ignition for the first time. But then now people are trying to apply magnetic field on top of it by these coils. So people have shot a number of these, and the typical finding is having a magnetic field improve your temperature by 1 keV-ish and boost your fusion yield by a factor of 2. So it's kind of appealing to add magnetic confinement to inertial confinement. And also there is the direct drive approach to fusion, which typically means you have a capsule, which is the red thing over here, and you shoot lasers at it. But again, people have been applying magnetic field by putting these coils around the capsules. So they also have additional magnetic confinement. Of course, they can do a cylinder instead of a sphere. But in all those approaches to magneto-inertial fusion, you have the situation where you have a bunch of lasers and also a magnetized plasma. And the magnetic field here is actually pretty substantial. For example, if you just wrap a coil, if you use a pulse power generator to drive a current, you usually can get to 10 Tesla very easily. So if you stretch it, maybe you can get to 50 Tesla. And if you really stretch it, you may get to 70 Tesla. So which may be very large by ordinary lab standard, but still very small by laser standard. Because here you're comparing the laser frequency with the gyro frequency. The laser frequency is enormously large compared to the gyro frequency. But the issue here is you're imploding stuffs. So if you learn about MHD, you know the frozen-in law. If you compress a plasma, you compress the magnetic field with it. So if you start with the, let's say, 30 Tesla field, and you converge by a factor of 10, then your area shrink by a factor of 100, then your magnetic field, roughly speaking, get amplified by a factor of 100. Then you all of a sudden have a kilotesla field, which then becomes really strong and really start to affect the laser plasma interactions. So laser plasma interaction is affected by magnetic field due to primarily four reasons. One is that obviously you put a magnetic field, you change the plasma condition. So you no longer have the same temperature and density you're talking about if you don't have a magnetic field. But on top of that, you also just change the linear laser propagation. Because if you remember, the laser is an eigenmodes in the plasma waves. And if you add magnetic field, the eigenmodes change and how the wave propagate change. And also, and that's on a linear level, but also more non-trivially, it also directly affects the nonlinear coupling between waves. And one of the most profound thing a magnetized plasma can do is to introduce a whole zoo of additional resonances. So if you learn about plasma waves, you may have heard the term there's a zoo of plasma waves in magnetized plasma, which are totally absent in unmagnetized case. So all these additional resonances will apparently complicate how laser and plasma interact. And so our goal is to study them with the goal to be able to control them, so people can really do the fusion experiment in the way they want. Okay, so in terms of understanding magnetized laser plasma interaction, I'll just abbreviate it as MAG-LPI. So this is a really underdeveloped area. So very few people have thought about how to deal with situations like this. So in the usual unmagnetized LPI, people usually use the ponderomotive picture to understand nonlinear interactions. So there, they think about two lasers. When they shoot into a plasma, they generate a beat wave. So that beat wave can ponderomotively drive a density fluctuation. So then you have a electrostatic plasma wave in the plasma. Then you're kind of having a grating now in your system. So then you can think about your lasers scatter off this grating. So that's roughly how people think about the unmagnetized version. So you have this grating, you generate side bands, and then you amplify these side bands. That's the usual kind of ponderomotive parametric picture of understanding nonlinear wave-wave interaction in magnetized plasma. But now, if you have a magnetic field, the grating isn't going to stay there. It's going to have a cyclotron motion on top of the wave motion. So then you have a much more complicated response than the usual ponderomotive response. So there is another picture that people can understand laser plasma interaction. I call that the parametric picture. So this is the process where you linearize on top of a background, right? If you remember, you're doing plasma physics, you have a background, you linearize, that's how you derive linear waves. But now let's say your background includes a pump wave, which is a laser, let's say, and then you linearize on top of that. So that's how some people derive the parametric coupling from that picture. But once you have a magnetic field, again, that makes things very complicated. Now your laser is like split into right-handed, left-handed mode. They're not degenerate anymore. And all the plasma response are getting more complicated. So there is another picture, which is a different way of thinking about the same physics. It's the scattering picture. So the scattering picture is usually taken in the Thomson scattering study of plasma physics, right? You can use Thomson scattering to measure different quantities in plasma, like density, temperature, and so on. So in those situations, you envision you have a laser shoot at the plasma, and there's some fluctuations in the plasma, and the laser scatter from these fluctuations. So in an unmagnetized plasma, the only kinds of fluctuation is actually density fluctuation, and of course associated other fluctuations, but they're all related to density in very simple ways. But for magnetized plasma, you can have other totally different fluctuations. For example, you can have Alfvén waves where you have magnetic fluctuations. You can twist your field lines, keep the density the same, right? So there are totally orthogonal ways you can fluctuate in a magnetized plasma. And when you shoot your laser at a plasma, they can scatter from all these different kinds of tensorial fluctuations. So finally, there's an approach I call the perturbative approach. So this is when you solve your plasma model perturbatively. So I think everybody taking plasma physics class have learned about linear waves. So what you do there is you linearize your nonlinear equations, right? So if you keep the lowest order, that's the linear wave. So the question is, what if you keep on going to the next order? So the second order will be the three-wave coupling. So a few years ago, we have a paper deriving how that works. And using that perturbative picture, we derived a coupling coefficient for the nonlinear wave-wave interaction. So the coupling coefficient appears in the three-wave equations. So these are nonlinear. So what this equation says is you have two waves. They can beat and generate a third wave of a different frequency. So it's a nonlinear process. And the coupling coefficient is measuring how strong that nonlinearity is, right? You can imagine coupling goes to zero, then you have linear waves. But coupling is large, then you have a strong coupling between them. So this coupling coefficient is the key parameter that controls non-linear three-wave interactions in the plasma. Okay, so we derived the formula, but what does the formula mean? So the formula tells us there are at least three distinct mechanisms that a magnetic field can affect laser three-wave scattering. So here I draw a Feynman diagram-ish thing here. It's actually, you can calculate this from a Feynman diagram. It's not schematic, it's actually true. But let's say you have a laser, which is the wave one, it shoots at the plasma, and then a laser scatters because it excites, let's say, current in the plasma. So the laser becomes some other wave, let's say the second wave, and the third wave is the plasma fluctuation that carries the remaining momentum from the system. Okay, so then you have a formula that relates the three waves. And in the formula, there's a key term I call the scattering strength, which looks like the wave vector, and the polarization vector is the E, and F is proportional to the dielectric, the susceptibility tensor. So essentially, if you know the linear susceptibility, you can calculate nonlinear scattering. So that's a non-trivial thing you can do. Okay, but in this formula, there are three ways the magnetic field can change the coupling. And the first thing you can do is to change the linear dispersion relations, namely change omega and ck. So one obvious thing is in unmagnetized case, the two electromagnetic modes, they are degenerate. But once you magnetize, they split into L and R. So that's for the laser. In addition to that, it also changed plasma resonances. For example, this is a fluid plasma. So you have those cyclotron-like wave, acoustic-like wave, or if you go to the low K limit, that's the Alfvén-like waves. So all these additional waves arise because you have a magnetic field. So the second thing you change is to change the plasma response, which is captured by the linear susceptibility. So here, the essential reason is now you have a gyro motion. Then the gyro motion mixes up somewhat the transverse electromagnetic wave versus the longitudinal density fluctuation. Now you're mixed, then you have a whole variety of them. So now you have a tensor response instead of a scalar response. And finally, magnetic field changes the polarization of all the waves. For example, if you shoot a laser that is linearly polarized, if the laser propagates parallel to the magnetic field, then you have the Faraday rotation. So your polarization is not going to stay the same. It's going to rotate as you propagate. And also, if you shoot with a perpendicular K, then you have this induced ellipticity. Namely, if you shoot a linearly polarized laser, the laser propagates and becomes circularly polarized at some points, or more generally, it's elliptically polarized. So if you change polarization, E, so three E's appear. If you change the plasma response, the F, and if you change the electromagnetic spectrum, the wave spectrum, then everything will change. And that's how magnetic field makes everything complicated, yet the very simple formula is able to capture all of these phenomena. So the question we ask is the formula correct? Is that too good to be true that it's very simple? Because usually if you look at papers people tried in the past derive magnetized nonlinear interaction, those are really lengthy formulas that don't look very simple. We have a very simple formula and we think that's correct. And the one way we show that's correct is to compare the theory with simulations. So here we want to do an apple-to-apple comparison, so we really nail down on everything. So on the theory side, previous pages I show you a three-wave equation, but to make things simple, we can sort of linearize the three-wave equation. The way we linearize it is by saying the pump amplitude is approximately a constant. So this is a good approximation. If your pump is much stronger than your seeds and your plasma wave, then it remains, roughly speaking, a constant. So once you do that, you convert a nonlinear three-wave equation to this linear coupled mode equation. So in these equations, there are some additional things that I was hiding before. One of them is the wave group velocity. So I should mention that having a magnetic field also changes the group velocity, but that's on a linear level. And also there's the damping. So the plasma waves damp both collisionally and collisionless damping. So here we are not talking about collision, we're just looking at collision-less damping, but still like Landau damping in unmagnetized plasma, you can still have similar phenomena in magnetized plasma, although they're much more complicated. So I do not know of a theory that can calculate Landau damping in a magnetized plasma when waves propagate at an oblique angle. So right now we just keep it as a parameter we're going to determine from the simulation. But on the right-hand side is the coupling coefficient gamma, if you I showed earlier. Now, if you multiply that by the pump amplitude and frequency and so on, you convert to a gamma naught. So gamma naught has the dimension of frequency, and physically that is the growth rate. If you have a constant amplitude pump, your C grows exponentially in that pump because of nonlinear coupling. So gamma naught is the growth rate.
Can I ask?
Yeah, sure.
Why do you call it a pump laser?
So this is from the laser amplifier community. Usually you have a pump laser that kind of excites your medium, and you have a seed laser that got amplified. So in
what is the excited state here?
so here the excited state is you
analogy?
excite the plasma wave. So alpha 3 here is the plasma resonance. So if you think of it as let's say the cyclotron resonance, you're exciting that. So the terminology came from the laser community.
And this is exciting at the frequency of the laser. Under motive.
So there are three frequencies here: omega 1, omega 2, omega 3. So omega 1 is the pump laser frequency which you set. For example, in experiment, you know your laser frequency. So omega 2 is the scattered laser frequency. This is something you can measure. And omega 3 usually satisfy the resonant condition. Then omega 1 equals to omega 2 plus omega 3. So there is a resonance condition. If that omega 3 happen to match the natural mode of a plasma, then the coupling becomes strong. If it's off resonance, they still couple, but it's much weaker. So here I'm looking at the resonant coupling case. Then in that case, you can think about your pump laser and your scattered laser, and their energy difference is consumed to excite the plasma resonance. So that's very analogous to a laser where you have a pump going to the excited state, and you lace and you have a medium that absorbs the difference. So here's the same picture.
And this is sort of just the general framework?
Yeah, this is a general framework.
So for example, for this plasma wave, is it linear wave or what kind of wave?
Yeah, so I will show you. Yeah, this right now it's for any waves. So any wave, if they can resonant interact, they're of this form. Okay, so in theory, obviously we can calculate gamma naught, but in simulation it's hard to get to it until you do something. So one thing you can easily do, for example, in a particle in cell simulation, is you do an initial boundary value problem. Namely, you initialize your simulation, let's say to be a quiescent plasma, and you shoot your lasers from the boundary and watch how the laser propagates and scatters in the particle in cell code. So here we have a plasma slab, which is the gray thing. So this is space and time. So the plasma just stays there the whole time. And then you have a pump laser first coming in from the right boundary. And then you have a seed laser coming from the opposite boundary. So these two lasers will overlap in the plasma. And if they hit a resonance condition, they will exchange energy between them.
So the pump laser with this omega 1, what is the seed laser here?
That's omega 2.
That's omega 2.
Yeah. Yeah. Okay, so we want to have our theory to match the simulation setup. Therefore, we want to solve the initial boundary value problem on the theory side as well. So initial value means at time t equals to 0, this is the spatial profile of the waves. For us, this means it's 0 initially. But then you have a boundary condition. So saying as x equals to 0, for example, here, you're shooting a wave. And at a later time, you dictate what happens at the boundary by injecting your lasers. That's something you dictate in your simulation. And if you look at the red boxes here, and this is how you can match apple to apple between a theory and a simulation. So the simulation, so here the pump has already filled up the plasma. So the plasma is kind of excited. You can think of it that way. But once you're done with that, then it's a linearized treatment. Now you send a seed laser and to extract energy from the excited plasma, roughly speaking. So then you have exact matching between your setup, between theory and simulations. But then we have to be extra careful because we're doing a kinetic simulation. So there are many things we need to be careful about. One thing I just mentioned is the damping rates. We actually don't know the damping rates. So you know the analytical formula for Landau damping, that's unmagnetized, right? You can try with magnetized. So if any one of you know, tell me. I would like to know that. Okay, but we don't know that. So we need to somehow determine both damping and growth from the same simulation. So that has to be carefully treated. And the way we do that is we take the transient time profile of the solution, which you can extract both parameters independently. So that's the important part. We don't know damping, but we can measure it. And once we know that, we can measure the growth rate. Okay, so the other thing is the three-wave equations. They are technically correct only for the eigenmodes. So in magnetized plasma, the eigenmodes are elliptically polarized in general. So if you launch a mode that is not an eigenmode, then you can think about it as linear combinations of two eigenmodes. But these two eigenmodes actually interact differently in magnetized plasma. So if you mix them up, then it's hard to tell what is what. So we do a very careful job to separate out the eigenmodes. So we're only looking at the eigenmode we're interested in. And also in kinetic simulations, your distribution function will also evolve. And once your distribution function evolves, that changes everything. So we want to watch for the simulation and only use the data where the distribution function hasn't changed very much. So that's a important thing we need to monitor. And finally, we're using particle in cell simulations, which has a lot of numerical noise. So the particle in cell code will spontaneously scatter even without a seed laser. So you don't want to get into the regime where spontaneous scattering is too strong that overwhelms your seed. So that's a bad place to be. So we try to be careful. So we're choosing parameters such that the stimulated is always stronger than spontaneous. So then we just ignore the spontaneous. Okay, so then I talk about the general field and what we're trying to do. I think we can go into slightly more details, although I'll probably skip some of the things. So one thing is we're going to solve the initial boundary value problem. If you heard of Laplace transform, that's how we're going to solve it. So I'm not going to show the details here, other than showing there is a formula that relates the initial condition A and the boundary condition H to the solution. So the key is a solution map, which is kind of like a Green's function thing. I'm not going to tell you all about that, but I'm going to show you that there is a key difference between forward scattering and back scattering because of causality. So here we're solving wave equations. So if you transform coordinate, they're just like the relativistic wave equation. So there's a causality, there's a light cone. So the light cone is between the two gray lines here. So there are three regions in front of the light cone, inside the light cone.
Okay. What are these things? What's shown here? What are X and V?
Okay, so here X and T are space-time.
Because we cannot read all of any of this, actually. Not just all of it, but any of this.
Yes.
It goes too fast.
Right, that's going too fast, but I don't expect you to read anything above that. But what I would want to know is the causality. Okay, so here we have two waves, I label them to be 2 and 3. So they have a group velocity, V2 and V3. So I'm just saying V2 has this, if you go at the group velocity, it's this dashed line. If you go at the other group velocity, it's the other dashed line. So in between them is the light cone. So this is the same light cone as in special relativity. So information can only propagate within the light cone, if you look at the equations. So in the forward scattering case, the two lasers are going in the same direction. So therefore, you have three different regions. So in front of the light cone, everything is predetermined by the initial condition. So this is the past light cone. The red cone is the past light cone. So the past light cone only intercepts space. So it only knows about the spatial initial condition. Similarly, the blue past light cone only knows about the boundary condition. So everything that happens here is determined by the boundary. But then you have the the green region where you know both the initial and boundary conditions. That's for forward scattering. But for backward scattering, the laser propagate in the opposite direction. So that's the situation we actually care. We propagate lasers in the back scattering geometry. So in that case, there's no blue light cone. There's only the red and the green light cone. For the green light cone means is the boundary condition and the initial condition, they are not independent. And the way to think about this is if you initiate some perturbation on the boundary, that perturbation is going to propagate left at this group velocity V3. At some point, that information will arrive at the boundary. So you cannot arbitrarily dictate the boundary conditions. So remember, now I have two waves. They have two boundary conditions. If you specify one of them, you cannot arbitrarily specify the other one of them. Otherwise, you'll get inconsistencies. So that's the important thing that we did, taking care of. Maybe people in the past didn't take very good care of. But then, so specifically, we're focusing on the backscattering condition. So there is a well-post condition for the backscattering case. So we're just going to do initially quiescent plasma. So it's the zero initial condition. And then we're having the laser enter through both boundaries. But the well-post condition means you have to be self-consistent with your boundary condition. So I don't think I will go into the details how this works, but it's sufficient to say that if you specify the laser boundary condition, then you cannot independently specify the plasma wave boundary condition. The plasma wave boundary condition L3 is totally determined by the laser boundary condition. So it's convolution with some Bessel functions and stuff, but it's determined. Okay, so you can only specify laser boundary condition, and that's what we do in peak simulation anyway. So because you specify boundary, you don't actually touch the plasma so much usually.
When you say specify the laser boundary condition, you mean like the tangential electric field at the boundary?
Yeah. So this is like you're coding up your Maxwell solver. You have to specify the last grid point, right? That's the boundary condition for the lasers. So we do specify that, but once we do that, we're not allowed to touch anything about the plasma. The plasma will self-consistently evolve such that the plasma boundary condition is fulfilled, which is given by the last formula here. So we don't touch the plasma. We just touch the EM fields. Oh, okay, so that's the setup at the very bottom. We have a pump laser, which is roughly a constant amplitude thing. And then we launch a seed laser. So the way we do that is we take a step function, it ramps up in time. So we can take other profiles. But in this particular profile, we have a simple analytic solution. I say it's simple because they're expressible in terms of Bessel functions, but Bessel functions are not very simple, I guess. But anyway, the thing is you can plot the growth function like this. So here V2 is the group velocity of the laser, which is approximately the speed of light. It's slightly slower because you're magnetized plasma. But then if you watch how the laser grows, as the laser front doesn't grow, because the laser front always encounter a fresh plasma. There's no resonance in there, so the front doesn't grow. Okay, but behind the front, after the laser stimulates emission, so to speak, the back of the laser will start to grow. So if you watch fixed, let's say you watch a fixed position in space, watch what happens in time. Before the laser passes, there's nothing. After the laser passes, you start to grow. So that's the stimulated scattering process. You just need to stimulate first. Okay, so similarly for the plasma wave delta 3, it looks slightly different, but the physical picture is when once the laser passes, then you have two lasers beating, and that can excite the plasma resonance. That's how they grow behind the wavefront. Okay, so that's how the solution looks like. But basically, we know the analytical form of the solution. So we can use the solution to feed simulation data. So that's what we're going to do. And in that solution, I just want to mention there are other parameters we care about. For example, there is a growth rate, gamma naught, which is what we are interested in finding. So we're going to feed the data to find gamma naught. But at the same time, there is the damping, which I told you we don't know. But then the damping appears somewhere, so you can also feed for the damping. So you can feed all the unknown parameters using simulation data once you have it. Okay, so that's the theory part. Now we can get to the simulation part. So as I mentioned earlier, we need to have very clean eigenmodes to avoid contamination. So this doesn't matter for unmagnetized plasma because unmagnetized plasma, the two modes are degenerate. They interact more or less the same way. But magnetized plasma, they become non-degenerate. An intuitive way of thinking about that is the electrons, they're going like right-handed with respect to B field. So if your laser is right-handed polarized versus left-handed polarized, you're going to excite different kinds of resonance. So the polarization does matter a lot for magnetized plasmas. But if you run a peak simulation, you know, there are some numerical dispersions which doesn't match your analytical dispersion. Okay, and also there are some density fluctuations in peak that's annoying, but that slightly changes your dispersion relation. So your numerical eigenmodes are never the same as your analytical eigenmode, although they should approach each other if you have increasing resolutions. Okay, but we have a finite resolution. So what we need to do is we need to calibrate what is the numerical eigenmodes. So we do some calibrations, and the way we know that's an eigenmode is if we plot the electric field in the transverse plane, we know it traces an ellipse, and an ellipse should not process or should not vibrate and things like that. So as you can see, it's not ideal. So the numerical eigenmode we feed is close to stationary ellipse, but there are some slight fluctuations of that, but we think that's small enough. Okay, the other thing we do is, because we use particle in cell simulations, the direct observables you have are the electric field, magnetic field, your particle distribution. So those are your direct observables. You do not directly observe the pump laser or the seed laser. They're all mixed up. So we need to separate them out by doing some post-processing of the simulation data. And one way we separate out the pump and seed is using what we call the Faraday filter. This is, if you have a 1D propagation, your right-handed rule, right? Your electric field cross B field is K vector. If you propagate the other way, it's the other. So the phase velocity knows about the direction of propagation. So the right-handed wave, I call it plus, is E plus VB versus the left is E minus VB. So you can separate them out because it's a 1D. Okay, so and then we need to know the envelope. So far, all the electric field has a fast oscillation part. That's the wave frequency part. But what the three-wave equation do is looking at the envelope of the wave. So we want to extract the envelopes. Okay, but once we do that, it looks something like this. So your simulation data looks like the black line, which has both the pump and seed. And once you separate out the pump, which is the light blue, the cyan line here, and then the magenta line here is for the seeds. So you separate them out first, and then you determine their envelope. So if we here, let's say the seed envelope has grown, and our scheme is able to capture that very nicely. So that's what we need. We need the envelopes. And the other thing we need is related to an earlier point at the resonance conditions. So you can have off resonance interactions, but here we're more focused on the resonant interactions, namely the difference in frequency between the two lasers happen to excite a plasma wave that is a natural mode. So the way we decide the numerical mode is do some scans. We watch how the seed grows, and we scan the frequency of the seed laser and determine this is the resonant frequency where we have the most energy exchange. But other than that, we have a resonance, and then we can start to feed the equations. So here is a typical data. The circles are extracted envelopes from the peak simulation, and the solid line are fitting of these data using the initial boundary value problem. So remember, we have an analytical formula for the initial boundary value problem. Here we're feeding the data to determine essentially three parameters here. So one of them is the group velocity of the laser. So that's something you can calculate analytically. Here we fit them because there's some numerical dispersion, which is slightly different from the analytical group velocity. So we fit that. And we also want to determine the damping rate of the plasma wave, which we don't know. But by feeding the data, we can determine that. And then we also care about the growth rate, gamma naught, which is the thing we really care about. So here's the procedure of the feeding. I would say by plasma physics standard, this is a very nice fit. So we have three parameters feeding all the data because we're trying to match the simulation to the setup exactly. Okay, so now we have a feeding procedure. We can measure the parameters. We also want to quantify the uncertainties. So here, the color plot, the x-axis is the growth rate. The y-axis is the damping rate. So here, you can imagine if you have a stronger damping, that may look like a smaller growth, right? So there's some kind of degeneracy. You may wonder, is the growth really that small, or is it because the damping is too strong? So you overwhelm the growth, right? So we want to be able to separate them out. So for and here we're plotting the residual fit. Basically, the redder the color is, the worse the fit is. So we want to be in the whiter part of the fit. So here for a cold plasma, let's say it's just 10 eV. So then the Landau damping is really small because your distribution function is really narrow. You don't have much of a tail to really damp the wave. So in that case, the damping is poorly constrained. It can be anything from 0 to 10 to the 1, but just in comparison to the growth rate, which is here, like let's say 10 times 10 to the 12, which is much larger. So the growth rate here is always well constrained. So you can't feed the data if your growth rate is too large or too small. So that's for cold plasma. So for a hotter,
when you say cold plasma, relative to what?
To 10 eV here. In this case, 10 eV. So if you have 100 EV, it's much hotter, so the damping is much larger. If you remember your Landau damping formula, that's exponential dependence in temperatures. If you just heat it up, then it's becoming strong damping more strongly. So in this case, we can actually constrain both the growth and the damping. So here you can see the landscape looks like it's tilted in that way. And this is because a stronger growth looks like a weaker damping and vice versa. But here, as you can see, we have a convex landscape. Namely, we can actually separate out their effects. If you start from the best field going up, you will see the damping is too strong. If you're going right, you'll see the growth is too strong. So we can actually constrain the two parameters separately. So that's very important that we can constrain them separately. Okay, so then, so to compare with theory, we mostly care about gamma. So we want to marginalize the damping. So then you have this 1D residual. So the dashed line will be the best fit of the data. And the black line here as reference is the analytical prediction. So at this plasma condition, this is how much growth you would expect. And numerically, this is how much growth you measured. Right, so there's a error bar associated with your peak data because there are fluctuations and so on. So here we define the error bar to be the width that doubles the minimum residual. So here, this is the error bar. So later on, I'll show a bunch of error bars. This is what they mean. Okay, I just said those things. Okay, then now we can now do some real comparisons. So here, this is a scan with magnetic field strength. So here, the x-axis is B field going from 0 megagauss to like 40 megagauss. So earlier there was a question about what resonance are you looking at, right? So we know the resonance from their frequencies. So for example, we can tell this is the cyclotron branch because you increase the B field, the frequency change almost linearly. So that's the cyclotron wave. And there's this Langmuir wave, which is relatively insensitive to the B field, right? As you change your B field, they stay pretty much close to the plasma frequency. Of course, in a plasma, these waves hybridize. So the wave have both Langmuir feature and the cyclotron feature, right? It has more Langmuir feature over here, more cyclotron feature over here, but during the crossover, they're really mixed up waves, the hybrid waves. Okay, so that's the wave we're looking at. We can look at their growth rate. So the analytical growth rate are the lines, the blue line and the dashed line. By the way, the color in the upper panel matches the lower panel. Okay, so one thing that people study for the unmagnetized laser plasma interaction is the phenomenon they call the Raman scattering. So that's mediated by the Langmuir wave. So at B equals to 0, all you have is actually here the Langmuir wave. So here you're looking at the growth rate due to the Langmuir wave. So as the B field goes stronger, initially it's probably not. Yeah. Okay.
So blue line is cyclotron and green line is Langmuir.
So the line here marks the branch.
Right.
For this branch, this part is the Langmuir wave. This part becomes the cyclotron. Yeah, the nature changes after the crossover. Yeah.
So in the top plot.
Yeah, so the top plot, the blue here.
The blue here.
Yeah, which is here, which is the Langmuir-like wave. Yeah, yeah. Okay, so here you're looking at the Langmuir-like wave. But as the field grows larger, this waves start to become more and more cyclotron-like. So at that point, you see the growth rate actually decreases. And if you go further, this branch becomes the cyclotron-like wave. So here, if you're looking at here, it's mostly cyclotron-like wave. So there you have a growth rate, but it's a smaller growth rate than your initially unmagnetized Langmuir wave, because actually now it's a cyclotron wave, to be fair. And here, looking at the dashed line, so initially, as B field ramps up, at B field equals to 0, there's no cyclotron wave at all. There's no such resonance at all. As the B field ramp up, the cyclotron waves start to mediate the laser scattering. So you'll see this branch ramps up. And during the crossover here, they actually have comparable growth rates. So here, during the crossover, there are two modes that have distinct real frequencies. But the imaginary part of their frequency become the same. So that's an interesting phenomenon. As you keep on ramping up your B field, so this branch becomes the Langmuir-like wave, right? So the way I remember it is the upper part is always Langmuir-like. The bottom part is always cyclotron-like. Right, so here now, if you have a magnetic field this large, then the Raman scattering becomes larger than your unmagnetized Raman. Okay, but that depends on your B field. In intermediate B field, you actually have smaller Raman scattering, but at larger B field, you actually have larger Raman scattering. So people sometimes ask, having a magnetic field, does it increase or decrease Raman scattering? So the answer is that depends on how strong a field you're talking about. It can be both. Okay, but the key thing here is the theory, which is the line, match the simulation, which is the symbols. They're almost right on top of each other. I would say this is a very good match by plasma physics standards. Yeah. Okay, so that's scanning the B field. We can also scan the propagation angle. So let me walk you through it. Let's maybe look at the real frequency first. So here I'm looking at the regime where this is 3 kilotesla, but maybe let me explain that. So initially, when theta equals to 0, so this is the cyclotron-like wave.
This angle between what and
So here angles between K and B. And so this is theta 0 means parallel propagation to the B field. So there's a cyclotron kind of wave, right? So as you increase the angle, so now you're becoming perpendicular propagation. So in this particular parameter choice, that wave becomes the upper hybrid wave, right? So it's a continuous wave branch, but people call this cyclotron wave when 0 degrees, upper hybrid when 90 degrees. Okay, so the other branch at 0 degree, that is the length mirror wave. So you have a length mirror wave propagating parallel to the B field. And as you increase your angle, it becomes more and more perpendicular, and that wave becomes the lower hybrid wave. So that's the lower hybrid wave here. Okay, so that's the real part of the frequency. So let's now look at the imaginary part. So at 0 angle, the cyclotron wave does not provide any coupling. An intuitive way of understanding that is a cyclotron wave is handed, has a right-handedness, has an angular momentum, right? So now if you want to exchange energy between two lasers, you have also exchanged angular momentum. Somehow that wave have to satisfy angular momentum conservation. So the cyclotron wave cannot do that because it's spin 1. So three-wave interaction, you have to conserve spin, so it doesn't work. So cyclotron wave therefore provides 0 coupling if you're exactly parallel. But as you increase the angle, the cyclotron wave get more and more electrostatic, then the coupling becomes larger. So this branch essentially ramps up as you go to larger angles. And at upper hybrid frequency, then you have a upper hybrid resonance, then it's totally fine to transfer energy through that resonance. So the other branch is the length mirror wave branch. So initially, the length mirror wave branch here is basically the unmagnetized Raman scattering, because now you're propagating parallel to the B field. So the magnetic field doesn't really do much other than changing the laser, other than split the laser frequencies. But this is basically unmagnetized Raman. As you ramp up in angle, so this branch will become the lower hybrid wave. So the coupling of that branch decreases. And an intuitive way of understanding that is the length mirror wave has dominantly charge fluctuations. The electron has a large part to it. But once you become lower hybrid wave, ions become a major part of it. So ions are much heavier. So if you want to couple through the ions, the coupling is weaker because of the heavier mass, essentially. Okay, so we can understand all that from theory. But the really nice thing here is the theory and simulation, again, they match almost perfectly. That means, so we have a correct theoretical understanding that does match the simulations.
And what are the error bars indicating here?
So that's the error bar I'm talking about here. So that's the width that doubles the minimum of the residual. And that's the error bar. If you define error bar differently, then you have a different size error bar. Okay, so that's the simulation for the electron-dominant waves. I haven't mentioned anything about the ion-dominant waves. So one of the reasons is it's difficult to do ion waves in peak simulations because it's too noisy. If you have any electron-dominant thing, they usually are much larger than ion things. So usually you would just have electron spontaneous response, overwhelm, stimulated ion response. It's hard to do that. But in some regimes, we're able to do that. For example, here, we're mediating the energy transfer between lasers via the acoustic wave. So maybe now let's look at the B equals to 0 case. That's the unmagnetized. So unmagnetized, you have the ion acoustic wave that can mediate energy transfer between lasers. People usually call that cross-beam energy transfer. So if you heat here we're scanning the frequency difference between the two lasers. So if you heat the acoustic resonance, then there is a large transfer. So here's the gain, and namely the output of the seed versus the input. Okay, so this is the unmagnetized acoustic gain. As you ramp up the magnetic field, keeping the temperature and density, everything else the same, you'll see the acoustic peak is reduced in height, but the location, central location of this is maybe slightly, I would say, slightly shifted to the left. So this is so once you magnetize, you no longer just have pressure compression. Now you also compress the magnetic field, right? So you imagine it become harder to compress both the thermal pressure and the magnetic pressure. So intuitively, you would expect that the coupling to become weaker because it's harder to move stuffs. But also there is another thing that the damping also actually increases as you also try to compress the B fields. So both effect works in the same direction, namely to reduce the coupling if you fix the temperature and so on. And the other thing I can do is you can look at the angles. So here, theta 20, roughly speaking, is parallel propagation. It's the blue line down here. As you increase the angle, you see the coupling first increase and then decrease back to the 90 degrees. So this is not a monotonic trend. So this is because you are observing both the damping and the growth at the same time. So they compete. So which one wins will determine how large a coupling you actually have. But the other more dramatic effect of a magnetized plasma is you have additional resonances. For example, if you remember about your waves class, there is a thing called a Bernstein wave, right? So usually people talk about Bernstein wave when you propagate perpendicular to a magnetic field. But of course, when you propagate at an angle, there is still Bernstein-like waves. I'm just calling that electron Bernstein-like waves. So those waves provide additional resonances. Here, the lowest peak is the acoustic peak. But very close to the acoustic peak, you also have those Bernstein peaks. So what that means for people who do experiment, they shoot laser across the plasma. Usually the unmagnetized plasma, they only worry about laser energy transfer mediated by the acoustic wave. Now, if you have additional waves, then you have to be careful about those additional resonances as well. So that's something that we are going to investigate more in the future. So that's about the theory. Oh, and I should mention this is kinetic simulation. It knows about the Bernstein waves. But the theory early on, I was trying to compare is the fluid-like simulation. So here, if you look at the resonance, you can see a fluid-like resonance typically looks like this, versus a kinetic-like resonance. You have a fluid peak, but you have additional peaks next to it. This is from the Bernstein waves. So I didn't mention that back here. Okay, so I guess I'm running out of time, but let me briefly mention some of the experiment, try to measure some of the effects. So one of the effects I mentioned is the polarization effect. Namely, if you have a magnetic field that change the way polarization and change how things couple. So for example, if you have an unmagnetized plasma, if you shoot two lasers, if their polarization vectors are orthogonal, then they do not exchange energy. So that's a well-known fact in unmagnetized LPI. But once you have a B field, that's no longer true for many reasons. One of the reasons is what enters your formula is no longer E1 dot E2, but E1 dot the tensor times E2. The tensor has off-diagonal components. Once you magnetize the orthogonally polarized laser, they still interact. So we're trying to set up an experiment at the omega laser to measure that. So the experiment we do is we have some targets, which you can't see over here, that produce a magnetized plasma. And then we shoot a laser across the magnetized plasma. And we have two diodes watching the scatter light from two directions. One direction is parallel to the laser E field. One direction is perpendicular to the laser field, E field. So if you think about the dipole radiation pattern, you would imagine you can observe scattering when you are looking perpendicular to the electric field, but you will see nothing if you're just looking along the E field, right? If you think about that dipole picture. So that's true for unmagnetized plasma. But once you magnetize, you no longer just have a dipole oscillation. You also have a cyclotron oscillation. Then everywhere you look, you have a scattering. So our goal is to measure that. So we did some measurements. So this is the case where we have no magnetic field. You see there's only a signal in only one diode, the orange one. And when we turn the B field on, both diodes is the signal. So that's roughly what we're expecting. But what we didn't expect are the background lights. If you see here, the signal actually shoots off all the way up. So that's it goes off the scale. It isn't shown here. And also we suspect some of these are maybe background lights. And if you look at the timing, that happens when the laser shoots across the volume and hit your chamber on the other side, and the chamber scatters everywhere. So we need to get rid of that. So we're still doing the experiment, but currently we're just putting some backdrop to block some of the background light. So that's one thing we're doing. And the other thing we're doing is to try to actually measure two laser beams crossing in a magnetized plasma, and they exchange energy. So here we're again doing at the Omega facility. They have a top 9 beam, which is a wavelength tunable beam. So what that allows us to do is to scan for resonances. So we can scan the frequency until we hit the resonance where the transfer is strong. So in peak simulations, we expect that for a magnetic field that can be produced by what they call the MIFAT, which is basically two coils, you drive a current through them, it produces a magnetic field. So that's typically 40 Tesla-ish. So if you just have that magnetic field, we expect this the acoustic wave mediated CBAT is not much affected. But that remains to be measured experimentally if that's the case. What we also want to see if there is additional resonance we can see, for example, from the Bernstein waves. So for that purpose, we need a much larger B field. So one way we make the B field is to use this laser-driven coil. So here you have a laser hitting a gold plate, and the gold plate is bent into a mailbox shape. So as the current flow through the bent section that produces a B field here. And then we're making plasma by having a laser hit a foil, and the foil ionizes and expand. We have a plasma jet. So from our experiment, we actually can see the plasma jet forming in this magnetized setups. But that's something we're currently doing. We haven't had a conclusive picture. But roughly speaking, we have a need to understand the magnetized laser plasma interactions. We have some theory about that. Currently, the theory passed the test of simulations in the fluid regime. So we're trying to push that into the kinetic regime. And also we're trying to do experiment to see if all those things match up with the experiment. And with that, I'd like to thank you for your attention.